Doesn't look like Mia's coming in for the meeting. All right, I should put up the screen. We're going to start gas laws. So we're going to do chapters 12 and 13 together as a combined chapter. We're done with chapter 12 if you watch the video on Friday. Okay, if you didn't watch the video on Friday, then you probably have some notes to take, but the rest of us are done. Okay. So when we talk about gases and behavior of gases, and I should probably pull up the actual notes for this, which are, I think, in a... No, it's a review. I'll get there. There. Okay. We found them.
Do you have any copy for this?
Yeah, I put it on your desk. Or is it right behind you? I'm sorry,
I had... This is somebody else's desk. I've got one seat up. Okay, well, thank you.
All right, so when we talk about gas laws and gases, they're dependent upon certain things. One of the things that they're dependent upon is the pressure. Another one is the volume and temperature. And then the last thing that they're dependent upon is the amount of gas present. Okay, so if you blow up a balloon, you have a certain amount of gas when you put your first breath in there, and then you have to catch another breath and blow it in there. You're increasing the amount of gas in there. Does that make sense? Every time you blow into the balloon, you're giving it more and more gas. Good? No? Okay. So gas pressure is due to the collisions between the particles and whatever container they're in. Did you have to write something down for that? Yeah. Okay. Okay. So you got that. One of the things that we're actually in a container ourselves. Okay. And I don't mean the building, I mean Earth. Okay. Earth is a container. We have an atmosphere. The atmosphere holds in the gas that's on Earth. Okay. Keeps it from floating away into outer space. And that atmosphere then, because of that and those layers of air that are on top of us, we actually get pressure at a certain level. So at sea level, the typical pressure amount is 1 atm. They call it 1 atmosphere. The pressure for the SI units, the metric, is in the pascals. And 101.3 kilopascals then equals 1 atmosphere. So each one of these things equals one another. Okay? And you can use those to convert from one to another. Let me see if I've got my gas pressure sensor. So we can actually see, I can actually show you what the pressure is. And pressure varies, atmospheric pressure varies based on your location. And you can actually look up, oh shoot, I need the, first class of the day where I'm doing this stuff. And I just go by, just kind of fly by the seat of my pants. There we go. Okay, so you can actually go online and see what the pressure is. Local conditions. Let's see if this will give us some. Yeah. So like right now in Janesville, it tells us that it was on the other screen. Let's change the format on here. That's weird. Over here, oh, it's off to the side. So off to the side, here it says that the pressure in Janesville. Let me see if I can. That's weird. Here it is. Okay. It says that it's 29.7 inches. That's the barometric reading. And you can do that for different places in the country. Okay. If we go to let's see if this will let us do Denver. Oh, it probably won't from there though, will it? Search. So it's 29.7 here. If we go to Denver, you can see that it's 30.06 there, which is kind of weird. You'd expect it to be less there, but it varies based on what your location is in the country. So, but that's in inches of mercury. So if we wanted to go from this to atmospheres, for example, we could use these as our conversion factors. Okay. So Janesville right now, it said that our pressure was 29.7 inches of mercury, right? So if I go 29.7, if this will let me use my pens again today, let's see if it's going to be nice to me. So 29.7. And that's inches of mercury that they gave us. If we wanted to see what that was in atmospheres, or let's do kilopascals, because that's our metric unit. I would use these as my conversion factors. Okay. I know that for every 29.9 inches of mercury, that I have 101.3 kilopascals. Okay, so I just use my dimensional analysis. These are my conversion factors because everything here is equal to one another. Does that make sense? So if I plug that into my calculator and I want to figure out in Janesville right now what that is, then I would go 29.7 times 101.3 equals, and then divide that by 29.9. That would tell me that my kilopascals was 100.6 kilopascals. That makes sense? And you can find these readings all over the place. If you look at your tires, for example, on your car, they're usually, 30 PSI. So on your car tire, around the edge of it, you will actually see, or your bicycle tires, it'll say inflate to this many PSI. But you could convert that PSI into atmospheres. And typically, that pressure is always going to be higher than what it is out here. That's why when your car tire goes flat, it's because it doesn't have enough pressure. You need to increase that pressure. Let's let's see here. If we look at the pressure in this room right now, we can actually measure that. I've got this Logger Pro here. I can drag it over. There we go. So this is the pressure in the room right now, and that's in kilopascals. So compare that to what we just calculated for outside atmospheric pressure, and it's a little bit different, okay? I think I can change this to, no, cancel. Sensors, data collection, set up sensors, here we go. Yeah, I can change this to different values here. So I can change this to PSI. I can change this to, so this is right now here in our room. So this tells us what our pressure is in the room here. So we can change it to inches of mercury. Okay. I can take a syringe here and I can actually measure the pressure in the syringe. Now, right now in this syringe, it's not capped or anything. So it's just the same pressure that it is in the room. So when I put this on, the pressure really shouldn't change at all. And it really didn't. But if I push down on this now, I'm going to increase the pressure. If I pull back on it, I can actually decrease the pressure a certain amount. Okay. So I can increase and decrease. And we'll talk about that more coming up in a few minutes. But that gets it, let's put this into atmospheres so that when we talk about this, we can have it in that unit, okay? All right, put him over here. So those are different pressure units. All right, pressure does not depend on the identity of the gas, and that is weird. Like when you think about it, you're like, so it doesn't matter if it's carbon dioxide or carbon monoxide or oxygen. No, if it's a gas, it does not depend on the identity. It's just the pressure, the temperature, how much material we have in there. That's what it depends on. Okay. So the first guy that we talk about, and he's a looker. Look at him. He is handsome as can be. This is Boyle's law. Boyle's law relates pressure and volume. And if we go back to this Logger Pro here, okay, and I take my, let's say that I have this syringe, I have this at 10 milliliters of air inside there, and I'm going to cap this, okay? So I have a certain amount in there. If I decrease the volume of the container, look what happens to the pressure. What happens? Did you see the value up there? I added a 10. I'm going to take it down to 5 milliliters. What happened to my pressure when I decreased my volume? It went higher, okay? If I take this from 10, there's 10. If I take this up to 15, I'm increasing the volume. What happens to my pressure? It decreases. So this is an inverse relationship. I have other terms for those. Direct, indirect relationship.
What did you do differently? Because earlier you were doing the same thing, but the numbers were going opposite.
Well, this is decreasing the volume.
Right.
And that the same thing happened.
Okay.
And this is increasing the volume. And it should increase or decrease the pressure.
Oh, so you're just measuring something else. Because earlier you were doing you would push it down and it would go.
It should go up when I push this down.
Oh, never mind. Ignore me. I don't know.
And when I pull this up, the values should decrease.
Okay, yeah. That makes sense.
Okay. So that is Boyle's law. And what he says is if you decrease the volume, your pressure goes up. If you increase the volume, your pressure goes down. So he's going to relate volume of gas to the temperature. Volume of a gas to its pressure. The temperature here remains constant. So temperature remains constant. This ends up being an inverse relationship. One goes up, the other goes down. So if pressure decreases, what has happened to your volume?
Pressure decreases. That means the volume is increasing, right?
The volume increased.
Is that what you were looking for?
Huh?
Is that the answer you were looking for?
Yeah.
Or is that something else?
No,
Okay.
no, it's as simple as that.
Okay.
One goes up, the other goes down. It's like a seesaw. One goes up, the other goes down. Were you guys allowed to play on seesaws? I don't know.
Yeah. It's just been a while though.
Well, they found them dangerous now, you know.
Really?
Yeah. Well, everybody's wrapped in bubble wrap now. You know, everything's danger.
I know.
Yeah. So.
Our world is just
Well.
very different.
Yeah. I mean, think about my world. Like, we didn't even have car seats when I was a kid. So we didn't wear seat belts. We didn't have car seats. Yeah. Now my kids wore seat belts and had car seats, but back when I was growing up, we didn't have any of that stuff. I mean, they were in the cars. They didn't have car seats, but they had seat belts, but nobody wore them. I mean, we rode in the back of pickup trucks, you know, when I was a little kid. Yeah, but I think now there's like a law you have to be 16 or older to do it, you know.
Oh, I thought it was just like you're not allowed to do it, period.
Well, I think it's 16 and older, but it could be. I don't know. I'm just saying, like, back in the day, like, you know, as kids, we rode in the back of pickup trucks and didn't think anything about it. So, all right. Now, this isn't as critical for this one, but you need to get started and get used to starting to write your volume in liters. It's not critical for this law, but in a couple days when we get to the ideal gas law, you have to, you're going to have it in liters. So it's a good idea to kind of get at least started in your mind thinking about, you know, liters and how to convert between milliliters and liters. So just kind of start getting that notion coming across in your brain. Okay. I think that's all you needed for this page. Okay. Oh, hello. We have all the answers here for you. Looks like. Let's get rid of that. We will work through these ourselves. I'm getting answers from last year. That's cheating. All right, so I always tell everybody to start out with the formulas. Like, just start out with the formula, and then you can figure out what you're going to plug in from there. Okay, so P1 V1 equals P2 V2. All right, let's identify what each of these things is. Okay. So this is our beginning materials here. Okay. So we're beginning with this stuff here. This is our starting amounts. So these are going to be our P1. This is our P1, our pressure 1. And I know it's pressure because it's given in kilopascals. And that is one of my units of pressure. Okay. And this is volume because it's given in milliliters. And I know that volume is measured in milliliters. Okay. So these are my beginning amounts. So this is my P1. What they mean by 1 is our beginning amount. Then we're going to go through a change. They say that they're increasing the pressure. So this guy right here, he's kilopascal. They also said my pressure is increased. So that's another hint that this is pressure. This is going to be my P2. So I'm going to sub these values in to my formula here.
So you don't have to do anything with the 188 though. Like you don't have to like subtract 99 from 188.
No, do not do that. Okay?
Why is that? Because don't you have
Because this is the formula. Like, no, don't. Just, the formula does not tell you to subtract. Do not subtract.
Oh, okay. I was just thinking because like it says it increased to that, so I was thinking that you're trying to figure out like you don't take.
They didn't ask you how much the pressure increased. They ask you what the volume's going to be.
Oh, okay, okay.
If they would have asked you what the new, you know, how much it increased by, then yeah, that's fine. But that's not what they asked you here.
All right. Thank you.
All right. Now, I'm going to plug these in. Now, some people like to isolate this variable first and then plug in. So if we isolated V2, V2 would equal P1 V1 over P2. So some people like to do that algebra with the formula first before they plug the number in. I don't really care how you do it, just as long as you get it done. Does it make sense what I did there? How I isolated this variable?
Yeah.
Okay. So now I'm going to flip around. I'm going to solve for V2. And I'm going to sub in what I have here. So P1 we identified up here as 99 kilopascals. The other thing that you need to make sure of is that you need to make sure that these pressure amounts here are in the same unit. If they're not, then you have to convert one of them into the other unit. So 99 times 300 milliliters. And again, you can change this into liters right now. You can keep it in milliliters, but eventually you need to get in the habit of converting to liters. All right, I'm going to divide this by 188 kilopascals. And then I'll have my answer. All right, so let's look here and see what's going to happen with our units. Our kilopascals are going to cancel out, and that's going to leave us with milliliters, which makes sense because we're solving for volume, right?
Okay. Okay.
All right, so if I do 99 times 300 divided by 188, my new volume is going to equal 100, and we need 3 sig figs because this is 3 sig figs. So 158, and that's going to be milliliters. So that will be my answer. Now, go back and make sure that this makes sense. Okay? So does this make sense? We did what to our pressure? We went from 99 to 188. We increased our pressure, so our pressure went up. So increase in pressure. What should happen to our volume according to Boyle's law? If this goes up, what should happen to this?
The pressure, the volume.
With the pressure increases, what happened to our volume?
The volume
decreases, okay? So did our volume decrease? We went from 300 to 158. Was that a decrease? Okay. Now, that doesn't tell you for sure that you got the right answer, but at least it's a double check to see if you're in the right ballpark. Okay. All right. Good? All right. So that's Boyle's law. Charles's law then relates temperature and volume. So the volume of a gas to its temperature. Your pressure here is going to remain constant. This ends up being a direct relationship.
Alright, so then we just write if the temperature. Wait, what happens if the temperature?
So this is a direct relationship.
Alright.
Okay, so direct means that if one goes up, what happens to the other one? No, that's indirect.
It goes up as well.
Right. So if the temperature goes up, the volume will also go up. So increase in volume.
Okay.
Good? All right. So let's try one of these. So here, oh, the one thing that you've got to be aware of. Now this, like, I'm not picky about the liters so much, but you have to have your temperature in Kelvin. If you don't have it in Kelvin, these problems will not work. You will not get the correct answer, ever, okay? So be careful with that. Remember that Kelvin equals degrees Celsius plus 273. I think, is that written on your sheet? If that's not on your sheet, get that on your sheet. Okay, you've got to know this. Okay, good. Okay, so let's go over here. So this one, again, the temperature is not in Kelvin. So we've got to automatically add 273 to this. So 273 plus 89 is going to get us into Kelvin. So 273 and 89, that's going to give us 362 Kelvin. So we're at 362 Kelvin. That's going to equal our T1. Our V1 then will have been right here. That's 0.67 liters. They want to know T2. We're figuring that out. And our volume 2 is 1.12 liters. All right. Our volume increased. So what's that going to tell us about this number here? Is it going to be bigger than or less than 362? So our temp.
I'm confused. What's the V1?
V1?
P2, P1, P2, T1, T2. It's supposed to be.
I think you're down at Gay-Lussac. We're just on Charles right now.
Oh, I'm just looking at the wrong equation. It's the same part. Okay, I'm sorry. Yeah.
All right, so this is, if we have T1 here, our volume increased. So what does that tell us is going to happen to our temperature? It'll increase, okay? So just as a general rule, kind of look at that and see, you expect this number to increase here. So we're going to figure out how much so it did, okay? So this is our V1 over T1 equals V2 over T2, okay? So I'm going to sub in what I know. I know that this is 0.67 liters over my T1, which is 362 Kelvin, equals My V1 is V2, excuse me, V2 is 1.12 liters over T2. So I'm solving for that, okay? So what I do here to solve for this is I cross multiply, okay? Or you can divide this out and then divide, yeah, so anyway, I just cross multiply. So this becomes 0.67 liters T2 equals 1.12 liters times 362 Kelvin. All right. So I'm going to multiply these two things together. So 362 times 1.12. And then I'm going to divide that by 0.67. And my answer comes out to be T2 equals 605. My units will end up being Kelvin because my liters will have canceled out. And then let's check this out. We said that our temperature should increase. It increased from 362 to 605. So that checks out. Good? Okay. All right. Let's move on to Gay-Lussac. He's our last named law for a person. Then we're going to have a combined gas law. We'll see if we get to that today. All right. So Gay-Lussac relates pressure and temperature. Okay. And this is pressure and temperature. The volume now will remain constant. This is a direct relationship. So if your pressure decreases, what would you expect to happen to your volume? Pressure decreases, volume would do what? Direct relationship. Well, it's not the temperature. Remember this? Yeah, temperature. Yes, it is. I'm sorry. Why did I say volume? That's why you're not answering me, because I didn't do it right. All right, pay attention better. Sorry. Sorry. I need to pay attention. All right, so my temperature is also going to drop. Okay? That makes sense? Makes more sense to you than it did to me. Sorry. All right. So here we have a sealed container. We have a pressure of 125 kilopascals. Our pressure is going to go up to 201. We're starting at 30 degrees Celsius. So again, we have to add 273 to this. So this ends up being 303 Kelvin. Okay. So this law, if we want to use, you can use whatever formula you want. These formulas are given to you, so you can however you want to use it. So P1 T2, if you cross multiply, that's what you get, and this would be P2 T1. That's a sad looking 2 there, or a sad looking P, I guess it would be. Let's try that again. Here we go. All right, so P1 here is 125 kilopascals. And again, you need to make sure that these are in the same units. If they're not, you got to convert one of them to the correct unit using the dimensional analysis that I showed you earlier. We are solving for T2. P2 was given at 201 kilopascals. And our T1, we calculated to be 303 Kelvin. Again, it has to be in Kelvin in order for these problems to work out correctly. So if we take 201 times 303 and divide that by 125, we end up with 487. So Chi2 equals 487, and that's going to be Kelvin. Now, does that check out? Okay, let's go back and look and see what happened here. This was 303 Kelvin. Okay, so our pressure increased. What happened to our temperature? It increased, and that checks out with Gay-Lussac's law. Okay. All right. The last one is a combined gas law. So we're going to take all three of these guys, and we're going to combine them into one fancy schmancy law. Okay. So here is the law. If we're given like 5 of these things, we can solve for the other one. Okay. And if you kind of like take volume out of the equation, you can see that. If you take pressure out of the equation, you can see Boyle's law. If you take temperature out of the equation, I'm sorry, you can see Charles's law. And if you take temperature out of the equation, you can see Boyle's law. And you can see how they come together to get this. All right. Oh, did you have to fill in stuff for that one?
Yeah.
Okay, I'm sorry. I'm
No,
sorry.
you're good.
Okay. You're
I
done?
should have started writing sooner.
Okay.
I was just trying to catch what you were saying. Okay, I'm good now.
All right. All right. So combined gas law then. Again, you need to make sure that all of your things are in common with their partners. So this is given an ATM. You need to make sure that this is given an ATM. If it's not, you got to convert. Okay. This is given in liters. We're solving. So when we solve, we'll end up solving in liters. These, they are Celsius, but they've got to be Kelvin. So we've got to change that over. So 36 plus 273 is 309. So this is going to be 309 here, Kelvin. And 28, this will be 301 Kelvin. So make sure that you convert those into Kelvin. All right, so P1, V1, T1 equals P2, V2, T2. So I'm going to start plugging in what I'm given. So here are my T1 values. So I'm going to plug these in to this side of the equation. So P1 is 0.998. V1 is 2.1 over 309, sorry, 309. Then my P2 is 0.900. I'm solving for V2, and then that's over 301. So we need to solve for V2 now. So if I take this and I cross multiply, over here, okay? That's going to give me 630. Oops, shoot, sorry. 630.8 equals, and then 309 times 0.9 is going to give me 278.1 V2. So I just cross multiplied. I multiplied this stuff and I multiplied this stuff. That's how I got that value. It's from here. And these guys I multiplied to get to here. Does that make sense? Now I'm going to solve for V2. So V2 is going to equal and I need 3 sig figs for this, so 2.6 or 2.27, and that's going to be in liters. So that would be my answer for this guy. Okay. So your homework tonight, I gave you a single sheet. I'll have more for tomorrow. I just didn't get the stuff printed out for you. So if you want to stop by, I might have that done after third hour if you want to stop by and pick up stuff for the next few days. But I didn't get it done before class, so sorry.
So
all right.
Is there something different for tomorrow that's in the packet?
No, that's what I was just, there's going to be more notes tomorrow. Okay, and there's going to be another, there's going to be another worksheet for tomorrow, but I don't have it printed off. I'll try to get it printed off third hour if you want to stop by.
I wasn't sure if we had like what we needed for tomorrow.
No, you do not have, you have the notes for tomorrow, but you don't have the homework.